In this next session, we move very firmly towards the application of those concepts for exoplanets. And unless NASA's budget increases substantially in the next decade, that means we're most definitely referring to remote detection, including radio, UV, HD+, and so on. One point I want to mention for this particular session is that in all cases, we're looking at coupled systems, be it looking at the impact of a planet on the activity of a star, or whether we're talking about radio emission from a planet. In all cases, we're referring to coupled systems, and understanding both the star and the planet and how they interact is very important. As an introduction to the interactions of planets and stars, there's no better place to start, I think, than a general overview of exoplanets, both their detection and characterization. And we have Wes Traub in the room, no better person to have here to give us an introduction to planets. And Wes is the chief scientist for NASA's Exoplanet Exploration Program, and given the successes in the last few years of Kepler and so on, I think it's a perfect person to give us that introduction. Wes.
Thank you. Thank you, Greg. Excuse me. Okay, I will talk about exoplanets. The word magnetic will not show up in my talk at all because this has not been part of what we've been thinking about, because it's not something that we can easily do with existing optical telescopes and whatnot. So you'll have to use your imaginations as to where we can measure a magnetic field as I go through the talk and tell you what actually is going on today. All right. Okay, so I will back up quite a bit because maybe some of you are not experts on exoplanets, and so I will start with the planets that we used to know. And as this says, you know, back when I was a child, there were 9 planets, but now there are fewer. Pluto got demoted, and that was the state of our knowledge. And a lot of these planets are things that I've worked on during my research career. So having exoplanets is really exciting. All right, but today, now I've got to start this thing because, come on, start. There we go. Okay, this is so cool. This is the planet Orrery that Dan Fabrici put together. It doesn't have all of the exoplanets that have been discovered. It's just got the number that fits onto this screen. And they're going around and around, and you can see the short period ones and the long period ones and the giant ones and the small ones. I mean, it's just fabulous wallpaper picture. And there's absolutely nothing scientific that I have to say about it. It's just that I love the image. So anyhow, there's lots and lots of exoplanets out there. And in fact, the number that we've been able to find has been growing with time. And if I can find the pointer, which is right here, I'll say, all right, so here we have years since the first exoplanet was discovered and the total number that have been discovered. And so this is a cumulative number, and so it's been rising. And what we're looking at here in blue is the confirmed planets, the numbers that have been, the planets that have been confirmed by having either radial velocity measuring them, which is pretty unambiguous, or transits plus some radial velocity, or Kepler, which is transits plus some radial velocity. Always to be confirmed. And also there are a few microlensing planets in here, and some from timing, and one from astrometry. Then from Kepler, there is a whole extra batch. This is additional numbers. This is on its own scale up here of about 2,000 or 3,000 extra ones that are called candidates that are not confirmed, and probably most of them will never be confirmed because the planets are too far away and too faint, the stars are too faint to be able to do the kind of confirmation that you can with a radial velocity check. So these are the ones we're absolutely positive about. The candidate ones, my personal opinion is that they have almost exactly the same degree of reliability as the good ones here, maybe minus 10% or something. So they're pretty good, and I personally count them in the pantheon of total planets. So where are these planets? I think it's interesting to look and see. So if this is the Milky Way, which is of course not our Milky Way, but it looks like what it's supposed to look like, and we're out here in the outskirts, some 10 kiloparsecs or so from the center, this is the area that I want to look at here. And so what you can see here is the blow-up of that small square, and this is in light years because I actually give these slides to other people too. Divide by 3 for parsecs. And you'll notice that all the planets that we know, almost all of them are off in this one direction, which is exactly the direction, of course, that Kepler is looking with its 100 square degree field. And the rest of the 40,000 square degrees of the sky has not been looked at so carefully, but there are lots and lots of planets here, all the way down to the Earth here. There's a few streaks going out here. This is the ones that have been found by Corot and other spacecraft that are looking in specified directions and waiting for transits to occur. So it's remarkable that there's a whole lot of space that has not been discovered. If you blow that up again, you can see that the neighborhood, which is about a 30 parsec neighborhood, is still down here, and there's a lot of planets even outside of that. And if we look even closer, this is the number of known planets that are around stars. And if we just add all the stars that are perhaps prime candidates for searching for planets on the X's, then we can see that there's a lot more to be discovered in the solar neighborhood. And the reason we don't know about ones in the solar neighborhood, which you might think would be the easiest place to search for planets because the stars are bright, is just simply because if you're looking for transits, you're only going to see 1 out of 100 or out of every 200, because that's approximately the transit probability for a planet out around the Earth's radius distance from the sun. And so 99.5% of the ones that are at 1 AU are going to be missed because you just simply aren't going to see them because of the inclination of the orbit. Or some of these stars just simply are not very good for doing radial velocity. You need to have spectral lines, and hot stars don't do it. And some cool stars are very difficult to look at. Anyhow, that's the picture there. All right, so as I alluded to, there are several ways of looking for planets. So just to run through them for reference, there is radial velocity. So you look at the star, and like I said, this was intended for a different audience, but you see the star shifted to the red, and then to the blue, and red and blue, and so on, and back and forth. That's the pictorial way of looking at it. There's absolute transits, and that's when you're looking at the star and you just wait for it to dim. Not that much, but by 100 parts per million. That's a transit of 80 parts per million is the Earth across the sun. And that's the way Kepler looks for things, and most of the planets have been discovered by this technique. There's microlensing, which goes the opposite direction. You're watching the star, and all of a sudden it gets brighter, and then it goes back to being faint. And you know about this. This is the technique that you use when you're looking, say, at the galactic center, and you see a couple 100,000 stars, and you wait for one of them to get brighter. And the reason it gets brighter is because there's a foreground star halfway between you and the background star that just happens to pass almost exactly dead along your line of sight, and it does a gravitational lensing trick for you because it takes the light that's coming from the background star and magnifies it towards you for a brief instant. If it's the star itself, you'll get this rise that goes on for about a month. That's what this time period is meant to be here. And then this little glitch here is a planet that is around the star, and when the line of sight happens to pass around that planet, you get an additional amplification because of the interaction. And you'll see a little blip that lasts about a day, it turns out, from the planet. So what you see is this broad, smooth thing, and then there's a blip on it, which indicates that there's a planet there. And several planets have been discovered by this technique, and some important extrapolations have been made because it's so rare. And it also will be a fundamental technique on the space mission AFTA, or WFIRST, that is coming up, that I'll talk about in the very end of the talk. And then there's direct imaging, which is where you're looking at the star. The star, of course, is wiggling back and forth in the sky if the planet is around it, but you see, excuse me, a planet illuminated by the star on this side, then that side, and so on. And if you can just take a direct picture of this, which is one of the things that I'm specifically interested in, then you can take pictures of nearby solar systems. And finally, there's astrometry, where you look at the star and you rely on the fact that there's a center of balance, center of mass between the planet, which is invisible in this case, and the star will oscillate back and forth in the plane of the sky. It's sort of the opposite, the orthogonal thing to radial velocity. So there's a scorecard that we keep up because we're required to sort of pay attention to NASA headquarters, and they like to keep score on things. And so this is what the number of total planets that have been discovered are from these different techniques, astrometry and imaging. You see there's not very many. Radial velocity is the traditional technique that planets were discovered at, and it's got a lot. Transits are a handful, but the real transit machine is the Kepler machine down here, which has gotten some 3,000. So that boosts the 1,000 or so verified planets, confirmed planets up, and the total is on the order of 4,000, which is absolutely stunning. Okay, so I said direct imaging of planets is something that I'm interested in, and the reason it's interesting is because you can get a spectrum of the planet this way. If you can separate the light of the planet from the star physically in the focal plane, then you can put a spectrometer on the planet and you can characterize the planet. And as a spectroscopist, that's what I like to do. So this is, in fact, we don't do this yet very much, but we have hopes, and so that's why what I'm showing you here is all space missions that are planned to do that. But the theory is that with a direct image, if you can see the planet separate from the star, you can pick out things in the atmosphere spectroscopically in the visible, and possibly in the infrared also. At least in the visible, you can see water vapor, oxygen, molecular oxygen, carbon dioxide at 1 micron, methane if it's abundant, like on the early Earth, cloud structures, because it hides some of the stuff, and you can compensate for that. If you can watch for the rotation of the planet and see a variation with time on a rotation period, you can see, at least if you're looking at the Earth, you can see the continents and the oceans alternating back and forth. The brightness, the colors will change with time. That'll tell you the length of day. You can estimate an average temperature because you know the insolation, and you can guess what the greenhouse effect from water and carbon dioxide might be. And finally, you can search for signs of life on this planet by looking at the indicators, which are primarily the temperature and molecular oxygen. There's no real life molecule that we can look for, but the products of life, the exhalations of plants, oxygen, which enables animal life, of course, are good signs of life. And so I'll always use just that word, signs of life. And then I threw in the word magnetic fields because, as you saw, there are some ways of measuring magnetic fields by looking at aurora on the north poles or south poles of a planet. But when you calculate these things, it turns out that these auroras, the aurora around the Earth at least, and even around Jupiter, is very, very faint compared to everything else that the planet has. So it's difficult, not impossible. So there are some missions that have been planned. There was the Space Interferometer mission. It's canceled, dropped. There's the Terrestrial Planet Finder coronagraph, which is the reason I came to JPL 8 years ago. That's been postponed. And there's the Terrestrial Planet Finder interferometer, which works in the infrared and was also postponed. So until the last couple of months, this has been a pretty dismal topic. However, things are looking up. So, well, I guess I'll get to that eventually. But let's do a little tutorial on coronagraphs. Coronagraphs are what allow you to look at a star and see a planet next to it. So here's the star, here's the planet. And we're back here with a telescope, for example, that one. And if you put a star shade, this is one technique, here's another technique. If you put the star shade out here, 30 or so meters in diameter, at a distance of 50,000 kilometers, and you orbit these things so that they're always looking straight at the star, then you can peek around the edge of the star shade, which is serrated to keep diffraction from overwhelming you back here with a bright spot. And you can see a planet sitting right next to it here. This is a very actively studied technique, and there is a group of scientists right now studying this for a future space mission. Here's the alternative method of doing a coronagraphy. If you don't have the star shade, but you have a telescope, and the telescope forms an image of the star, you put some sort of gizmo at the focus of the star here, or you put something in the pupil of the telescope or in the image of the pupil of the telescope. And what happens in some cases is that the starlight, which is going to go through and now is fully illuminated here, the scattering from this thing by diffraction or by diffraction, period, tends to make anything that is exactly on the center of the mask splay out to the sides. And that's why there's a thing called a Liot stop here, named after Bernard Liot, who invented this when he was looking at the corona of the sun back in the 1920s and 30s. And so this blocks all the starlight that's on the dead center of the aperture here, goes off to the sides, and you can calculate exactly where it is. And what's left in the middle of the pupil is stuff that has hit this stop not on center, but off to the side, which is where the planet is, okay? So you put the star in the center, the planet's off to one side. Most of the planet light gets through, you can image it. Most of the starlight gets thrown away. So those are the two theories of coronagraphs. So currently, what are we thinking that we can do for exoplanets? So you know about Kepler, and as of now, it basically has completed its mission. You know that it had 4 reaction wheels to guide it in space. One failed last summer, another one failed this spring, and just this last week they finished doing the tests of those 2 wheels to see if they could be brought back to life, and it looks like they will not be able to be brought back to life. So we only have 2 reaction wheels, so we'll have to do other science. We cannot aim very accurately with just 2. So it may be that Kepler is at its end, and that this number will grow because there's plenty of analysis to be done on the data that's in the can, but it will not observe any longer probably. So we have ground-based things and space-based telescopes. I'll talk about both. I just want to mention that TESS is a transit experiment that was just approved this spring. George Ricker at MIT is the PI on it, and it'll search for transits just like Kepler did, but over the whole sky, over the whole 40,000 square degrees. And then the big thing that's coming up is what was called WFIRST, which was recommended by the 2010 Decadal Survey on Astronomy, and is now called AFTA, and probably will change its name again at some time. And the whole idea here is that it has on board a gravitational microlensing technique that you saw, plus now has been added a coronagraph for direct imaging of planets and disks around stars, a whole different topic. And the mission start is to be in October of 2016, and a launch in 2024 is the current idea. Okay, so what are some data on planets? Okay, here is from Kepler, radius versus period plot. So here's the radius in units of Earth radii, and here's the period in days. And 1 year is sort of slightly off the graph here. So you can see that Kepler is seeing things that have a lot of short periods. There's plenty of planets there, like Mercury, big surprise, of course. Off the graph is Jupiter's and so on at, not visible here. But there's plenty of Earth-like, and if you wish to have your definition of Earths or super-Earths stop at a radius of 2, then everything below this line here is an Earth or a super-Earth, and these are in the Neptune category. There's a lot of points on this graph. The points are missing in this region here just simply because there aren't. This is an extremely well-studied period, short period, large diameter thing. There are none here to speak of, relatively speaking. And there are none in this lower right-hand corner, and certainly down here, because Kepler just simply has a cutoff which goes something like this due to its sensitivity, its diameter, the photon rate, and so on. Another thing you can plot is radius versus distance, not distance from the star, but distance from the Earth, just to see if there's any biases in the data. And so you can see here that Kepler goes out to about a kiloparsec, and things are pretty much uniformly splashed around in that cone that you saw earlier. And again, there's a cutoff here due to the sensitivity of things being farther away. So that's the basic raw data these days. You can take that data and look at the planets that actually have masses and radii measured, which are transits or ones that have, there's several different ways of measuring mass and radius simultaneously or sequentially. And the dots here are where they are. You heard this morning that there are planets bigger than Jupiter. Jupiter's up here around 10, and there are some that are scattered up here. And the thought is, it was mentioned this morning by Dave Stevenson, but also that these are from young stars or young planets, and they still haven't completely gravitationally collapsed, or they may be being heated, irradiated from the star. So there's a lot of scatter up here. The solid curve is just an empirical curve that I drew through all this data with the least squares fit. And the reason it peaks here and goes down and comes down over on this side where the brown dwarfs live is that there's an electron degeneracy in a big gas object, and things just start getting squished. And so instead of growing larger and larger, as you might expect with a rigid solid, they start to collapse again, and you end up down here. And then after a while, stars take off and go up there. So someday I'll finish this curve by putting other things over here. But this is the empirical fit, and there are some things that stand out that are just absolutely not on the general trend, which need to be explained. This is a similar plot, mass from converting the radii into mass using that curve. That's the red spots here from over a year ago from Kepler. I didn't update it. And period down here. And the habitable zone, which is a goal for a lot of the work in exosolar planets, which is not necessarily a really strictly scientific thing to be looking for, planets that are the size of the Earth, that are in a region around the star where there could be water vapor and therefore could have life on them. This is not something you will see in an astrophysics textbook, but it is something that the taxpayers are interested in, and we are beholden to the taxpayers, and we're actually hopefully normal people, and so we should be interested in seeing if are planets that have life on them out there. And so this is the region where you could have life, okay? Up to up to 10 times the mass of the Earth, or 2 times the radius, a little bit below to capture Mars at one end, and then the inner and outer edges of the habitable zone. Outside of that zone, you can't have liquid water on the ground. So this is where all of this data is going, and we spend a lot of effort trying to extrapolate into this region. I mentioned that there is a space mission coming up now it's called AFTA, and this shows the contrast, which is the ratio of the planet brightness to the star brightness and separation in arc seconds. So this is the kind of graph that we use for coronagraphs. Contrast, for example, of the Earth. If you stand way back from the solar system and look at the Earth and the Sun, the ratio of the brightness of the Earth and the visible to the Sun is about 1 × 10⁻⁻10. So the Earth is somewhere on a line here, it's actually at 1/10 of an arc second away if you're at 10 parsecs away. So the Earth would be about here for a star at 10 parsecs. Putting randomly, these are computer-generated planets. You see a lot of giant planets here. They're Jupiters and smaller. And the small ones here, I've added, the white ones are Earth-like things that are scattered out there. This is compared with the sensitivity range of AFTA, which is by definition a 2.4 meter diameter telescope, so that limits you in angular resolution, and the amount of light that you collect limits you at the bottom end here, and how low you can go in contrast, how faint you can go compared to the star. And so we're limited to this upper right-hand corner, and the real question in AFTA as we work on it is exactly where these dividing lines occur and how sensitive we can make the emission. But the more sensitive we can make it, the more likely it's going to go down towards Earth's and just barely begin to nick the edge of where Earth's might be found. I would say it's unlikely because this inner angle here is pretty well fixed by the diameter of the telescope. But we can certainly find Jupiters, which are at about 10⁻⁹ or so in contrast, and at 1/2 an arc second, so a Jupiter would be right about at this edge here. So we should be able to pick those up.
Is this for a solar type star?
These are all stars in the solar neighborhood. We're also interested in disks and the zodiacal light, you may ask, and the Kuiper belt outside of the solar system. The zodiacal light would translate, if it was the same on all stars as it is in our solar system, into this blue line, which is not very visible here. And then farther out in the solar system, when you get to Jupiter and beyond, there is the Kuiper belt, which should be about this bright. So they're sort of competing, but not wiping things out. That's the good news. So I'm into yellow already. How long has that been there? There are a number of things that we can do on the ground. I will therefore not go through these telescopes. There are experiments at Palomar that are going on to search for planets. There is the Very Large Telescope, which is going to have an instrument called SPHERE on it, which is going to search for planets. There are several experiments that have been done. This is HR 8799. The star is hidden here, and there are 4 planets, B, C, D, E here, just barely visible. Ground-based experiments have been done to look at the spectrum of these planets. Very difficult experiments. This is another spectrometer measurement in the near-infrared that was made at Palomar, indicating that there is CO in the atmosphere, but not CO2, which is kind of a surprise there. This is semi-relevant to the meeting. This is a paper last year saying that the speculation was that Jupiter controls sunspots, or the magnetic field of the sun is connected to a planet, and I think this is something interesting we should bring up later during the meeting. This just plots, again, contrast versus separation for where the planets live, the Jupiters and the Earths, and all of the current ground-based limits. And so ground-based limits are not sufficient to get to real Jupiters, and these have to be done by a space mission, is the message of this plot here. There are a number of space missions that have been discussed. I mentioned a few at the very beginning. The only one that I'll really focus on, this was the Starshade 1, and the only one that I will focus on is not shown here, so I won't focus on it. Okay. There are all sorts of coronagraph concepts, masks that I mentioned. Here is a mask for the pupil. Here is a mask, a sort of straight line with bars next to it for the image plane. Here is a vector vortex mask that could go in the image plane. And there are test facilities at JPL and other universities that can do that. We already did the coronagraph idea here, but we'll move on. One of the key technical elements with these things is deformable mirrors, mirrors that are, in this case, about 48 by 48 millimeters square, and you can deform the surface by up to about a wavelength of light by pushing on piezoelectric thingies on the back and compensate for errors on the primary and the secondary mirrors of the telescope, which is crucial for getting these high contrasts. Here is a experiment in the lab where the star was here, and we've isolated the dark hole region, so-called, around it, and this is very dark at the 10 to the minus 9 and 10 level, so that one could search for a planet living in this area here. And we've reached 10 to the minus 9 and 10 to the minus 10 with different spectral bandwidths is the message from here. And I'm now in red, and I think I'm almost at the end. This is to emphasize what I said in the beginning, that there are a lot of small planets. If you add up the things that are Earths and super Earths up to 2, that comes out to a graph point that's here. And so you can see in the units that have been chosen to be plotted here that there's many more small planets than there are large planets, which is the essential message here. And there are a number of things that Kepler has done, but I will skip. I think there's 3 slides here and 4. Since the chair has not pulled me off yet, I'll talk about this slide for a second. This is interesting because this is a planet which apparently, it's a picture, of course. You know, the idea is that there's a planet that has an average density that is greater than that of iron. And how could you do that? Well, you could start with a Jupiter with a core and then strip off all the stuff on the outside if it was really, really close to its star, which is why it's drawn this way. And this might be of some interest to us here in this workshop. And we have a program, and finally, AFTA is going after microlensing, like I said, and high contrast imaging, and altogether that will produce something which tells us a lot about stars. And that's the end of my talk, so thank you very much.